Welcome to this discussion about solving linear and nonlinear inequalities. Okay, so sometimes we have linear inequalities that are quote unquote special. And that happens when either there's no solution to them, there's nothing that would actually satisfy the inequality, or everything on the real number line would satisfy it. And we recognize these inequalities when you're solving through the linear inequality and the variables are eliminated. There's no variable anymore, and all you're left with is an inequality statement. And you want to examine that statement to see whether it is true or false. So, when you're solving a linear inequality, and the variables are eliminated, and you have a remaining inequality that is a false statement, that means there's no solution. Okay, there's nothing that you can use for that x value that will satisfy the inequality at all. Okay, but then the opposite is also true. If you're solving a linear inequality and the variables are eliminated, and what remains is an inequality that is a true statement, then your solution is all real numbers. It doesn't matter what number you choose, it will always be true. Okay, so let's solve these two inequalities, and we're going to use this knowledge in order to state our answers. Okay, so similar to what we've done before, we're going to get rid of this 3 on the outside by distributing it through. So we'll end up with 3x plus 3 is greater than 3x plus 2. Now if I subtract 3x on both sides, I'm left with this inequality that says 3 is greater than 2. And that's where you have to stop and think, is 3 really greater than 2? And of course it is. 3 is definitely greater than 2. This is a true statement. And this means that everything I sub into this inequality will be true. So our answer is negative infinity to positive infinity. Now, I want you to think about this logically. Okay, what this is really saying is I've got some number that I'm going to triple. I'm going to multiply it by 3. And that number that is now the product that you've multiplied by 3 is here and here. Now, it doesn't matter what number that is. If you add 3 to it, it's always going to be greater than if you add 2 to it. So it doesn't matter what value you have for x, it's always going to work. And that is what makes this inequality have a solution of all real numbers. All right, so let's look at this one. Let's go ahead and distribute that 3 through. So we have 3x plus 1 is less than 3x minus 12. Similarly, we're going to subtract off the 3 x's, and we will have the statement 1 is less than negative 12. Now, sometimes these can be tricky because you have to kind of really think about where these numbers are on the number line. 1 is here and negative 12 is over here. 1 is not less than negative 12. We need to remember where the negatives are on the number line, and so this is a false statement, which means there are no solutions. And you would just leave your number line blank because there's nothing on it. So if you're really thinking about what's going on, you've got this number here. It's 3 times some number, but it's the same as right here. And you're adding 1 here and you're subtracting 12 here. Well, obviously you're going to have more on this side, and this is saying I'm going to have less. So there is definitely nothing that will satisfy that inequality. Okay, and the last thing we'll do in this video is talk about solving compound linear inequalities, and this is what we see when we've got multiple inequalities happening at the same time. Okay, you'll see more than one inequality symbol existing, and what you're going to want to do when they're all together like that is you're going to want to isolate the variable found in the middle here. Here's where you're going to find the variable. You're going to isolate it. Now, every isolating step you use, you are going to apply to all three pieces of the inequality. You're going to apply it here on the left, here in the middle, and here on the right. Everything you do. So let's concentrate on this middle for a second, and you're looking at this expression 3x plus 5. What would you do to isolate the x? Well, the first thing you would do would be subtract that 5. So let's subtract a 5 in all three places, okay? So let's subtract a 5 on the left. That would give us negative 15. In the middle would give us 3x. And on the right would just give us 5. And so we're left with a simpler inequality. But we still have that 3 that is encumbering our x. We want to divide out that 3. So let's divide it out on the left, in the middle, and on the right. So if I divide out the 3, here I have negative 5. This means it's gone. And on the right, I've got 5/3. So I've got negative 5 is less than or equal to x, which is less than or equal to 5/3. So what this statement is really saying is, I'm interested in all the numbers that are both greater than negative 5, so everything to the right of negative 5, but at the same time, they've got to be less than 5/3. So everything that is less than or equal to 5/3. Okay, so it's going to be all those numbers in between them, but including the endpoints. Okay, so it's going to look like this on the number line with the brackets on the end and everything highlighted between those two numbers. And then as an interval, you're just going to write it with the endpoints and the brackets because of the equal signs. All right, let's do this last example. So again, let's focus our attention to the middle of this inequality. And if we're going to isolate the x in the middle, we're going to want to add 2 everywhere. So adding 2 to this negative 17, to the negative 3x minus 2, and to the negative 14, we will end up with negative 15 is less than or equal to negative 3x, which is less than or equal to negative 12. Now I am going to want to divide out this negative 3 everywhere. But what did I say there? I'm going to divide out a negative 3. That means I'm going to have to reverse those inequalities. So when I divide out a negative 3 here, I'll get positive 5 is greater than or equal to x, which is greater than or equal to 4. So this is our answer, but when we have a compound inequality, we always want to write it from least to greatest. So we want to think of this as turning this whole thing around. So the lesser number is on the left and the greater number is on the right. But when we do that, we want to reverse the inequality symbols again, because I'm flipping the whole thing around. We want to say that 4 is the least, right? So that inequality will be pointing to the 4 even if we push it over here. So it's going to look like this. 4 is less than or equal to x, which is less than or equal to 5. Okay, and then our interval is everything between 4 and 5 because we're thinking of every value greater than or equal to 4, but at the same time less than or equal to 5. And on the number line is just this little tiny segment here, everything that's greater than 4 or equal to it and less than or equal to 5. Okay, that wraps up this video, and in the next video we're going to talk about how do we solve polynomial inequalities. I'll see you there.